Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator, the number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers and their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean.
Hi, and welcome to this video about angles. Let's start by defining a ray. A ray is a line with a single endpoint that extends infinitely in one direction. If we take this ray and add another ray to it that has the same endpoint, we've created an angle. We've also created a vertex, which is the point where two rays meet. You can think of it as a corner. We usually see vertices whenever lines meet or in polygons like triangles and quadrilaterals. Sometimes we have many angles, so in order to tell them apart, we have a system for naming them. Here's our simple angle again, but with a few points added on the rays. Now we can refer to our angle as angle ABC. When naming angles with 3 letters, the vertex point must be in the middle. Here, B is the vertex, so the B goes between the A and the C. We can actually call this angle CBA, and it is just as correct. If the point that is the vertex is only a part of one angle, then we can use a shorter name. In this case, we could also call this angle B. Be careful though, because sometimes a single point can be the vertex of multiple angles, like this. In this case, we'd have to call the angles by their long names, because point B is the vertex of angles ABC, DBC, and DBA. If we asked someone to just look at angle B, they wouldn't know which of these we meant. So it's important to be precise when dealing with more than one angle. Sometimes angles will be labeled with numbers inside the arc, like this. Now we have an additional name for this angle. We now call it angle 1, or we can call it angle ABC, or we can call it angle B. Since most of us have 3 names, it's only fair that angles have a bunch too. But most of the time, we like to use letters to name our angles, since the numbers could be confused with the measure of an angle. Sometimes you'll see lowercase letters instead of numbers, or Greek symbols like theta or alpha. Speaking of measuring, remember the protractor? We use it to measure angles. If we were to place one on our trusty angle, we would find that it measures 45 degrees. If we wrote this out, we would write it like this. The measure of angle ABC equals 45 degrees. The measure of an angle is important in classifying angles, as we're about to see. Let's look at a variation of our 2-ray angle, but this time let's make it so that they are perpendicular to each other, which means the angle between them is 90 degrees. Here, we've created a right angle. Notice that it has a different angle symbol than our first angle. Instead of an arc, it has a square. Whenever we see an angle with that square, we know it is exactly 90 degrees. We most often see right angles in squares, rectangles, and right triangles, but they can appear in other places too. When an angle has a measure that is smaller than 90 degrees, it's called an acute angle. Our original angle would be part of an acute triangle, since it measures 45 degrees, which is less than 90. If we make an angle so that it has a measure that is greater than 90 degrees, we create an obtuse angle, which looks like this. In this case, angle ABC has a measure of 140 degrees, which is greater than 90. Obtuse angles also have to be less than 180 degrees. Those are the 3 main types of angles as determined by measure, but there are 2 more oddballs we need to know about. The first is a straight angle. It looks like a straight line and it has a measure of 180 degrees. When it's drawn like this, we can see that angle ABC does exist and has a measure of 180 degrees. This is a useful thing to know because we'll need it to understand linear pairs later on. But before we get to that, let's look at the other oddball. This one doesn't look like an angle at all, but in fact, it's called a full angle. Imagine we rotated point A counterclockwise, with point B staying where it is, until it lined up with point C again. How many degrees is that? It's all the way around the circle, which we know is 360 degrees. Remember our straight angle? What if we drew that but added another ray sticking out of it, like this? If we know that angle DBC is 55 degrees, and we know that angle ABC is a straight angle, and therefore 180 degrees, we can actually find angle ABD. How? By taking the whole straight angle, ABC, that measures 180 degrees and subtracting the smaller angle, DBC, that measures 55 degrees. 180 degrees minus 55 degrees equals 125 degrees. This is called a linear pair. 2 angles, ABD and DBC, combine to form angle ABC, which is a line. And because the 2 smaller angles add up to 180 degrees, we can also say that they are supplementary angles. Something very similar happens with right angles. Here's our right angle from before, but with another ray in the middle. Angle DEF is a right angle. We can see that angle DEG and angle GEF together completely fill angle DEF, which means they add up to 90 degrees. So if we know one of the two angles, we can find the other one by subtracting its measure from 90 degrees. For instance, if angle DEG is 30 degrees, then we know that angle GEF is 60 degrees, because 90 degrees minus 30 degrees equals 60 degrees. Angles that add up to 90 degrees are called complementary angles. Let's go back to our obtuse angle one more time. There's one more type of angle that's been hiding in plain sight that we need to be aware of. We can see that angle ABC is an obtuse angle, which means it's more than 90 degrees and less than 180 degrees. But what about the other side? This is called a reflex angle. It's always more than 180 degrees and less than 360 degrees. Every acute, right, and obtuse angle has a reflex angle. Next, let's take a look at where we'll see some of these angles in the wild, or at least in geometry problems. Let's start by looking at two lines that intersect. In this case, we've numbered the angles. Whenever we see a figure like this, if we know any of the angles, we can determine all of the others. So if angle 1 measures 130 degrees, we can figure out angle 2, because those two angles together form a line and are a linear pair and supplementary. So angle 2 must be 50 degrees. The same works for angles 1 and 3. And then we can use what we know about angle 2 to pair it up with angle 4 to find that angle. When it's all said and done, it looks like this. Notice that the angles opposite one another have the same measure. These angles are called vertical angles, and they're always congruent, which is geometry speak for having the same measure. Now, let's look at three lines intersecting. This is called a transversal. Once again, we've numbered the angles and there are red arrow marks on two of the lines, indicating that they are parallel. A transversal doesn't have to have parallel lines, but when it is, it allows us to know a lot about the 8 angles created by the intersecting lines. But before we get to that, let's look at the 8 angles. We can see they are in two groups of 4, angles 1 through 4 and angles 5 through 8. Angle 1 is in the top left position in the top group of angles. If we look at the same spot in the bottom group of angles, we see that angle 5 is in the top left spot for that group. That means that angles 1 and 5 are corresponding angles. So angles 2 and 6 are also corresponding angles because they're in the top right spot for their respective groups. Angles 3 and 7 are also corresponding, as are angles 4 and 8. In a transversal, when there's a pair of parallel lines, corresponding angles are congruent. When the lines are not parallel, the corresponding angles are not congruent. In the case of our diagram that does have parallel lines, if we know that angle 2 is 55 degrees, we then know that angle 6 is also 55 degrees. And once we know that, we can use what we learned about vertical angles and linear pairs to find all the others. That's all we need to know to find our angles, but there is some more location-based vocabulary we need to be aware of with these types of problems. Interior angles are the angles between the parallel lines. In this case, that's angles 3, 4, 5, and 6. The exterior angles are the ones that, you guessed it, are not between the parallel lines. So angles 1, 2, 7, and 8 are exterior angles. Alternate angles are angles that are on opposite sides of the line that cuts across the parallel lines. And same-side angles are angles that are on the same side of that line, of course. In questions about the two groups of angles, this is used to combine interior or exterior with alternate or same-side angles. The question will always relate to the other group of angles. Something like, what is the alternate interior angle for angle 3? We would look to the other group of angles, then to the other side of the intersecting line, and then find the only angle that is an interior angle, which would be angle 6. The same side interior angle for angle 3 is angle 5. That's a lot to absorb in a small amount of time. Try these questions to see if it's sunk in. What is the alternate exterior angle to angle 8? The answer is angle 1. What is the same side exterior angle to angle 7? The answer is angle 1. What is the corresponding angle to angle 5? The answer is angle 1.
Hi,
Hi, and welcome to this video on the properties of exponents. Working with polynomial, radical, and rational functions oftentimes requires us to perform algebraic operations with powers. Recall that a power is nothing more than a base that is raised to an exponent. So let's take a look at the properties of exponents that are used to simplify algebraic expressions with powers. The product of powers property applies to powers with the same base. When asked to multiply powers with the same base, simply add the exponents. For example, b squared times b cubed equals b to the fifth. This rule makes intuitive sense if you expand each power like this. B times b times b times b times b. Counting up the bases of b that are being multiplied results in 1, 2, 3, 4, 5. b to the fifth. Therefore, the general form of the product of powers rule is b to the m times b to the n equals b to the m plus n. The quotient of powers property also applies to powers with the same base. However, the rule requires the subtraction of exponents. Let's look at an example. B to the fifth over b cubed in expanded form would look like this. b times b times b times b times b all over b times b times b. Canceling out common factors of b from the numerator and the denominator would simplify to be b squared. The quotient of powers property allows a quicker, more efficient result. Simply subtract the exponent of the denominator from the exponent of the numerator. 5 minus 3 equals 2. The general form for quotient of powers property is b to the m over b to the n equals b to the m minus n. The power of a power property allows us to raise a power to another exponent. Once again, expanding an expression makes understanding the rule a bit easier. Suppose the power b cubed is squared. In expanded form, it would look like this. b times b times b times b times b times b. Using the product of powers property, or simply counting up the bases of b, results in b to the sixth power. The general form of this property is b to the m raised to the n equals b to the m times n. Expanding on the power of a power property results in additional tools that are used to simplify expressions with powers. For example, suppose the base of a power is a monomial with a coefficient and a variable. 3b to the fourth power squared expands to 3b to the fourth power times 3b to the fourth power. Rearranging the factors to group the coefficients and the powers with the same base, b, and simplifying gives us 3 times 3 times b to the fourth times b to the fourth equals 9b to the eighth. This is called the power of a product property and illustrates that the exponent of each factor in the base must be multiplied by the power outside the parentheses. The general form for the power of product property is b times c to the x equals b to the x times c to the x. The power of quotient property is similar in that the exponent of a rational base is multiplied by the exponents in both the numerator and denominator. Let's look at some examples. B cubed over c squared, all of that squared, expands to b cubed over c squared times b cubed over c squared. The product of powers property results in the simplified expression b to the sixth over c to the fourth. However, applying the power of quotient property directly is often more efficient. B to the third over c squared squared equals b to the 3 times 2 over c to the 2 times 2, which equals b to the 6th over c to the 4th. Here's another example. 2b over c squared d cubed expands to 2b over c squared d times 2b over c squared d, one more time, 2b over c squared d. Rearranging factors and applying the product of powers property results in 2 times 2 times 2 times b times b times b all over c squared times c squared times c squared times d times d times d. This equals 8b cubed over c to the 6th power times d cubed. If we were to apply the power of quotient property, it would look like this. 2 to the 1 times 3 times b to the 1 times 3 all over c to the 2 times 3 times d to the 1 times 3, which equals 2 cubed times b cubed all over c to the 6th times d cubed, which equals 8b cubed all over c to the 6th times d cubed. The general rule for the power of quotient property is b over c to the x equals b to the x over c to the x. As you can see, these rules are essential in simplifying expressions within our work with various algebraic functions.
Hi, and welcome to this review of the Pythagorean Theorem. We're going to go over how to use it properly and also go over some special triangles called Pythagorean triples that could save you some time when taking tests. So, let's get started. First things first, what is the Pythagorean Theorem? The Pythagorean Theorem is a squared plus b squared is equal to c squared. Now, this is used to find the length of a side of a right triangle when we know the length of the other two sides. The triangle has to be a right triangle, which means that it has an angle that measures exactly 90 degrees, like this one. The theorem is very easy to remember and just as easy to use. In the theorem, A, B, and C are the lengths of the three sides of the triangle. But which is which? Let's start by figuring out where to find A, B, and C in a triangle. To start, you can tell that you're dealing with a right triangle because you see this little square in one of the angles. That's the symbol for a right angle or 90-degree angle. And any triangle that has a right angle must be a right triangle. So now we have to decide where to put the three side lengths. The key is to start with c, which is always on the side across from the right angle. This is called the hypotenuse, and it's always the longest side. You may be asking yourself, if c is always across from the right angle, how do I tell which of the other two is a and which is b? It's a good question, and the answer is, it doesn't matter. Either of these two sides, which are called legs, can be used as a and then just use the other one for b. Let's pick 3 centimeters for a. And our b will be down here, and we know that's 4 centimeters. So this is what our theorem looks like when we have it filled in. 3 squared plus 4 squared is equal to c squared. Now we can just evaluate 3 squared and 4 squared, which means multiplying 3 times 3 and 4 times 4 to get the following. So now we have 9 plus 16 is equal to c squared. So, what's that? Little addition tells us 25 is equal to c squared. Now, here's where it gets a little tricky. We know that c squared is equal to 25, but we want to know what c is, not what c squared is. So, how can we get rid of that little 2? Well, we use the inverse or opposite operation of squaring something, and that inverse operation is the square root. Since it's an equation, whatever we do to one side of the equation, we must do to the other. So I'm going to take the square root of both sides. The square root of c squared is c. And the square root of 25 just happens to be 5. Look at that. It's always good to check our answer to see if it makes sense. Since we're finding c, it should be longer than any of the other two sides, and 5 is greater than both 3 and 4. Also, because of the triangle inequality theorem, which is something we'll get to in a later video, the hypotenuse must be less than the sum of the other two sides, which means 5 has to be smaller than 3 plus 4, which it is. So you might have noticed that the answer to this problem was a nice, neat integer, 5. This is actually kind of rare if we look at random triangles, but it's not rare in a math problem you might see on a test. It happens whenever a problem uses a Pythagorean triple. The triangle we just looked at is the most common kind of a 3, 4, 5 right triangle. The legs measure 3 and 4, and the hypotenuse is 5. Sometimes it will be disguised by multiplying all the numbers by 2, which means we would get a 6, 8, and 10. Or multiplied by 10, which means we would have a 30, 40, and 50 lengths. Or maybe any other number. You don't need to know this to solve a Pythagorean theorem problem, but it's a nice shortcut to save you some time or allow you to check your answer another way. Other Pythagorean triples include 5, 12, 13, 8, 15, and 17, and 7, 24, 25. There are many more, but these ones are the ones you will see most often. Of course, there are right triangles that aren't Pythagorean triples. Let's look at one just so you can see what the answer will look like. Once again, we're solving for the hypotenuse, the longest side, which is opposite the 90-degree or right angle. This is length C. When we plug in 5 and 7 for A and B, we get this. (25 plus 49 is equal to c squared. So let's add 25 and 49 to get 74, which is equal to c squared. Then we take the square root of each side and find out that the square root of 74 is equal to c. Now, even though 74 isn't a perfect square, this is the answer. If you take the square root on a calculator, you only get an approximation of the answer, which is about 8.60232526 forever. We can do this approximation to do our checks. It's greater than either of the other two sides, and it's less than the two sides added together. But when writing the answer, we should use the square root form.
It's been said that a picture is worth 1,000 words. This is true of the many different ways that data can be transformed into visual representations for easier interpretation. Data in and of itself can be difficult to explain, but when it is carefully organized, patterns can be revealed, or it may become apparent that no patterns exist. Either way, both results are meaningful. Advances in technology enable us to collect and track data like never before. An interpretation of data is simplified with the use of graphs. Data is collected for many reasons, ranging from simple consumer surveys to track preferences, to election polling, to predict the winner of a political office. Graphs are used to make that data easier to digest or comprehend. Before we get to the graphs, you should know that there are different types of data that can be collected. The first one we'll talk about is qualitative data. This data would result from a survey that groups respondents by category. For example, you can survey students in your school and ask them to report their eye color, gender, area code, and favorite movie type. These categories provide information for your study. In this case, maybe you're wondering whether there is a relationship between the number of blue-eyed sci-fi fans living in a particular area code. Well, you may be able to detect a pattern in the counts, or percentages, of qualitative data by category. Graphs that are used to depict qualitative data are pie charts and bar graphs. A pie chart looks exactly like what you might expect, a pie. A circle representing 100% of a particular variable of interest is divided into categories. Segments of the pie represent a percentage of the whole. Pie charts can also show counts. In this example, 6 people, or 30% of the respondents, favored romantic movies. Bar charts also show counts or percentages by category, but in a different way. It looks like a city in the distance with skyscrapers at varying heights. This bar chart shows categories on the horizontal axis with the associated counts on the vertical axis. Next, we have pictographs. As the name suggests, a pictograph provides visual context. Visual cues and images are used to represent the data, and keys are provided to tell you what each image or symbol represents. In this survey of student fruit preference, apples took the lead with 20 students reporting them as their favorite. Another type of data that can be collected is known as quantitative. Unlike qualitative data, you can do math with quantitative data because it is numeric in nature. For example, what if you're interested in the average AP statistics score of the graduating class of your high school? Gathering reliable data may be the trickiest part of your study, but a histogram can relay trends in the results with precision. A histogram resembles a bar graph, with the exception of spaces between the bars. There's a range of numeric values displayed on the horizontal axis, and the counts of students are displayed on the vertical axis. The pattern of scores may appear somewhat symmetric, which is typically referred to as normally distributed. This would suggest that most students scored in the middle of the range, and that there were some high achievers and others who were not so successful. A histogram could also show a skew to the right or left, which may reveal information about overall student understanding. Scatter plots show data points for 2 quantitative variables on the same graph. The pattern revealed could show an association between the 2 variables. The data is analyzed with respect to direction, form, and strength. Direction can be positive if a rising pattern is seen in the data, or negative if a falling pattern is seen. The form of the scatter plot identifies whether the data appears somewhat linear, curved, or cone-like in shape. Strength associates how tightly the points are gathered. An example of a strong positive, somewhat linear pattern could be revealed in a scatter plot of shoe size versus height of male high school students. Because typical male students continue to grow during the high school years, the data for all male students would likely show underclassmen data points at the lower end of the scatter plot and upperclassmen represented at the higher end. Data points that do not fit a recognizable pattern are referred to as outliers. Finally, a scatter plot with no pattern at all is also of interest to prove no association between the two variables. Regression analysis can be performed on scatter plot data that has been characterized as strong linear in shape and either positive or negative in direction. This regression line serves as a predictive model only for estimating other points of interest within the range of the data set. Line graphs are very useful to recognize how patterns in data sets change over time. Unlike a linear regression model that runs through a set of points, a line graph connects the data points. The graph of mobile phone sales over time shows an overall increasing pattern. However, there was a noticeable dip in the sales between 2011 and 2012. Graphing multiple variables together in a line graph can also be very informative. For example, suppose temperature and rainfall amounts in a particular region were graphed simultaneously. As can be seen, contrasting weather patterns are revealed. Finally, stem and leaf charts contain actual data values. The pattern revealed is similar to that of a bar chart that has been rotated clockwise 90 degrees. The stem of the chart lists the digits of an indicated place value vertically. In this example, the stem represents the tens of a data set of ages. The leaves branch outward with the digits of the ones place for each age in the data set. A key should always be part of the graph so the data can be interpreted correctly. This data set shows a pattern that seems to be skewed left towards the younger ages. There are 19 people under 20 and only 7 people over 50.
Hi, and welcome to this review of the unit circle. In this video, we will go over what the unit circle is and what it is used for. Before we get into the unit circle itself, let's talk about degrees and radians. Most of the time when you measure an angle, you measure it in degrees. For instance, a right angle has 90 degrees, a straight angle has 180 degrees, and there's an angle for every number in between. But there's actually another way you can measure an angle, and that's by measuring in radians. Measuring in radians relates the angle to pi, so pi will be in almost every angle measure when measuring in radians. Since pi is the ratio of a circle's circumference to its diameter, it makes sense that we use radians most often when working with circles. As most of you have heard before, a circle has 360 degrees. It also has 2 pi radians. Think of radians and degrees like centimeters and inches. There are 2 different forms of measurement, but they can be used to measure the same thing and can be converted between. The conversion used for radians and degrees is 2 pi radians equals 360 degrees, or if you simplify that, pi radians equals 180 degrees. Let's say we want to convert 270 degrees to radians. What we're going to do, so we're going to take our 270 degrees and multiply by our conversion factor, which is pi radians over 180 degrees. This then simplifies to 3 pi over 2 radians. Now let's try an example converting from radians to degrees. Let's look at pi over 6 radians. If we multiply this by our conversion factor, we're going to multiply this time by 180 degrees over pi radians, which then simplifies to 30 degrees. Now let's look at how this relates to the unit circle. A unit circle is a circle which has a radius of 1 unit and its center is at the origin. This may seem fairly common and you might be getting excited if you think I'm going to ask you to find the circumference or area. With a radius of 1, that wouldn't be very difficult. But today we're going to look at this circle through the lens of trigonometry. Trigonometry is the study of how a triangle's sides and angles relate to one another. Now you're probably wondering what circles and triangles have to do with one another, and that's a great question. One of the most common uses of trigonometry is in finding the measures of an angle given 2 sides of a right triangle. If we look closely at our circle, we can actually find right triangles in it. Here's an example. We know the radius is 1, and we can use SOHCAHTOA to find that the opposite is 1/2 and the adjacent side is √3. The unit circle is a collection of the most common right triangles, so we use it to remember the trig values of the most common angles. The coordinate points where the measure of a specific angle hits the circle gives us our sine and cosine values. For example, with a ray coming from the angle 60 degrees, the point that ray hits the unit circle is at 1/2 root 3 over 2. The x-coordinate gives us our cosine value for that angle, and the y-coordinate gives us our sine value. If you need to find the tangent value, simply put sine over cosine, or the y-coordinate over the x-coordinate. Going back to our example of 60 degrees, the sine of 60 degrees is root 3 over 2, our y-coordinate. The cosine of 60 degrees is 1/2, our x-coordinate, and tangent of 60 degrees is root 3 over 2 over 1/2, which simplifies to root 3. An important thing to note when discussing these angle measures is that the angles must be in standard position. Standard position simply means that the vertex of the angle is at the origin of the circle, and that one ray of the angle is on the positive x-axis. The other ray of the angle is placed at the angle measure formed by traveling counterclockwise along the circle. If an angle is not in standard position, it is important to place it in standard position before using the points to find your trig values. I want you to try to find a couple trig values on your own using the unit circle. For now, we will put it on the screen so you can refer back to it, but eventually you may want to memorize it since these values come up frequently in mathematics. Number 1, cosine of 180 degrees. 2, sine of 2 pi over 3. And 3, tangent of pi over 4. Go ahead and pause the video and see what you can come up with. Let's check your answers. The cosine of 180 degrees is -1, because at 180 degrees, the ray hits the circle at the point -1, 0. The sine of 2 pi over 3 is root 3 over 2, because it hits at the point -1/2 root 3 over 2. And the tangent of pi over 4 is 1, because the ray hits the circle at the point root 2, root 2. And root 2 over root 2 is equal to 1. Remember, you can convert between radians and degrees using the conversion pi radians equals 180 degrees. We then use our unit circle with angles in standard position to find the trig values of common angle measurements. I hope this review was helpful. Thanks for watching and happy studying.